So this question, we have to, and you're going to see this quite a bit. The two triangles are going to, in order to, and just in general, as we move throughout the rest of the course, they're going to have pictures with congruency marks in them all over the place. And they're going to have expressions all over the place. Okay, now this one, you could maybe say, I have absolutely no idea what to do, but I'm trying to solve for x and y, and that you just say, okay, well, I'm going to set the two things that have x in them equal each other and solve. Which is okay, that works here, but on like a test or quiz, I might give you another expression down here, and now you don't know, do I take 7x plus 3 and set it equal to 9x plus 9, or do I set it equal to the one that Mr. Fay added, okay? So what I want to do here is I want to write a triangle congruency here for us, because this goes back to what we learned in section 4.1, is that because we have side, 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 we should know that triangle ABC is congruent. So if I go A to B to C, I should be able to start at, what letter down here? If I started at A up here, I got to start at D, because remember, A is between 2 marks and 3 marks, right? So I got to do the same thing here. Now you went down the segment that had 2 marks in it, right? So where do I got to go from D to E? So triangle D, E, F, right? So remember what that tells me. That tells me that AB, first 2 letters here, are equal to or congruent to those 2 letters. And then BC is congruent to EF. And then AC is congruent to DF. Remember that? It also tells us that angle A is congruent to angle D, angle B congruent to angle E, and angle C congruent to angle F. Remember that? Okay? So, all of these things are true because of what we talked about yesterday, day before, CPCTC, right? Corresponding parts, congruent triangles, congruent. So we know the triangles are congruent. We know that those corresponding parts are congruent. Now, we can combine that knowledge with what we've got going over here. They're saying AC is 7x plus 3, and DF is 9x plus 9. Well, AC and DF, that was one of our congruencies, right? So we can set that equation up, that 7x plus 3. 7x plus 3 does indeed equal 9x plus 9, and we can solve that for x. Is that okay? We can then do the same thing if they ask us for y, because y is dealing with these angles, and we got angle E and angle B, so we're going to set those two equal to each other, so I got 6y minus 27 is equal to 93 plus y. Does that make sense? Okay. Now, that question, like I said, because of how they structure the picture, you could have absolutely no idea what to do and maybe guess, I got to equate the expressions that have x in them and equate the expressions that have y in them. I will eventually start to add information into these, okay, that you have to be able to decipher this information before you can set up the correct equation. Okay, so just want to make sure that we're all on the same page with that. So that was 21, I think. Were there other ones there that you said you had concerns about? Okay. Okay. So this one didn't ask you to find the angle?
Wait, yeah, what's the angle?
It's like find out, it's the first one.
So like you'll find x and then plug it in. No, like for 22.
So okay, so you type your answer in. Okay. Is this something, do we need to do another example or?
Yeah, the one where you have to find the measurement of the angle.
Okay.
Yeah, so you find like the y and do the same thing with the y.
Let's talk about that as well. So the nice thing about this one is, and they might have done it on the last one, but I didn't cut it out. They're telling you that these two triangles are congruent right here in the directions, right? And it is because side, side, side. So they ask, what is the measure of angle E? Well, angle E is that middle letter right there, so that should match up to B, right? So E and B, I have algebraic expressions for those, so 75 plus Y equals 4Y minus 30. I'll subtract Y from both sides and add 30 to both sides, so it gives me 105. So then Y should be, what is that, 35? So Y is 35, does that make sense? So now, they don't ask what Y is, right? They ask for angle E. So I come back up here and I say, okay, well, 35 needs to go there for that Y. And then subtract 30 from it. So 4 times 35 is, what, 140? And then minus 30 should be 110. So that angle will be 110. Does that kind of make sense? What would this angle B be? 110. And you can check that by taking 75 plus 35, and it does indeed give you 110. So that finding that 110 multiple ways kind of confirms that we have the right answer there. Is that helpful? All right. We're going to, if you printed out the notes, there's a lot of notes there. I know you guys have said they're bulky, but it's because there's a lot of like additional proofs through here. I'm going to, we'll get to some of these, just not today. Okay, we'll come back to them later on. We'll get to section 4.4. Usually section 4.4 I don't deal a whole lot with because the main concept is CP/CTC, which we have already been dealing with. So a lot of these things that you have in your notes are not necessarily linear in how we're going to approach them. We might jump back and forth from them as we go through the next couple days. Okay, but I think it's important to talk about the conclusion that gets made from knowing these triangle congruencies. Does that make sense? All right, so 4.5 is what we call the isosceles triangle theorems. What is an isosceles triangle? Okay, so at least two sides congruent, and you can also phrase that as two or more sides congruent, right? Okay. So at least two sides congruent, okay? So now my question is, what is an equilateral triangle?
All sides are the same length.
All sides are the same length, all three sides, right? So is an equilateral triangle also isosceles?
Yeah.
Yes, it is. 100% of the time. Is an isosceles triangle always equilateral? No, not necessarily, okay? Now, here's why I asked this before we get into these theorems. Because an equilateral triangle is 100% always isosceles. It has to be isosceles before it makes the condition or gets to the condition of being equilateral. Everything that we learned today about isosceles triangles can be then extended into being a truth about an equilateral triangle. Does that make sense?
Yeah.
Okay. That being said, we're not going to have a section that is devoted to characteristics about equilateral triangles because as we move through, we learn about the individual triangles like an isosceles that an equilateral also is. And then we just attach those properties to the equilateral. All right, so couple vocabulary words here, kind of broken down into a picture. A vertex angle is going to be the angle that is created. This is only in an isosceles triangle or a equilateral triangle. It is the angle that is between what we call the legs of the triangle, the isosceles triangle, okay? Or it's the angle that is created by the two congruent sides, okay? The two congruent sides, we call those legs, okay? Now, a lot of shapes have legs, okay? Or we refer to a lot of things that, shapes that have legs. So we talk about, like trapezoids have legs, isosceles triangles have legs. So it's a good thing to say that these are the legs and then say of an isosceles triangle. Okay. We have a base. Okay. Lots of shapes have bases. So this is the base of an isosceles triangle. Okay. The base angles are the angles that are created by a leg and the base. Okay. Or the two angles that are touching the base or formed by the base. Okay. Are called base angles. So I'm going to use those those terms throughout the rest of the course. Vertex angle is a very common phrase that we're going to use over and over and over again that people struggle with. Okay, usually everybody's okay with legs, everybody's okay with base, everybody's okay with base angles. It's vertex angle that they struggle with. Okay, is it okay? We good with that structure? All right, so we get to what we call the isosceles triangle theorem. Okay, and this is additional information that we're going to be able to use to do algebraic problems. It's going to be additional information that we use inside of proofs. But this is one of the most premier theorems and concepts in a geometry course. Okay, it says the isosceles triangle theorem says if two sides of a triangle are congruent. What does that mean? If two sides of a triangle are congruent, what does that create for us? An isosceles triangle. Okay, so if in front of you have an isosceles triangle. Okay, that's the condition that you meet. Then the angles that are opposite those sides are also congruent. Okay, the isosceles triangle theorem says if two sides of a triangle are congruent, okay, then the sides or the angles opposite them are also congruent. So that's a leg, right? That is a leg, correct? Okay. So it's saying in an isosceles triangle, okay, the angles that are opposite the legs are congruent. Well, what did we just refer to that angle and that angle as?
The vertical.
We called those the base angles. We called those the base because this was the base, right? Okay. So sometimes, I'm just trying to give you some alternative ways that you're going to hear me say this phrase, deal with this theorem. If, and I'm going to say if an isosceles triangle, so if that's what you have in front of you, then base angles are congruent. Okay, so instead of saying the angles opposite the legs or angles opposite the congruent sides, a lot of times you might see them just say base angles. Okay, because they're the same thing. Is that all right?
So it doesn't really matter, I know it says opposite, so when they say that, are they meaning this one and this?
Yes.
So that it doesn't really matter?
Yep, right. So when we say opposite, it's the idea that if I'm either standing on this angle here, okay, what's a word for something that is right next to me? Beside or adjacent, because those are words for being right next to each other, right? So would you guys agree that if I'm at C, that side right there and that side right there are beside me, or right next to me, or adjacent to me? If I'm standing at C, does that make sense? So what is the only side that I haven't discussed yet, or that I haven't highlighted? It'd be AB, right? AB then, by default, because it's not adjacent to angle C, it doesn't help make angle C, that is what we refer to as the opposite side then. Does that make sense? Okay. If another way of thinking about it, if I'm standing at angle A, and I want to get to this side over here, I have to travel through the inside of my triangle. Okay, and if you have to travel from a vertex through the inside of your triangle to a side, then you're traveling to the opposite side of that angle. Okay, does that make sense? And I know some people struggle with that terminology of opposite in regards to a triangle.
Yeah, when do you want me to take my quiz?
Oh, good question. You want to do it now?
Sure.
All right, So the isosceles triangle theorem, what I want to do is I want to prove this. Okay? So we have this. This is the information that we're going to start off with in regards to our isosceles triangle. Now, if we look at the given there, that is the if part of the previous theorem. The previous theorem said if two sides of a triangle are congruent. Well, if I'm giving you a triangle ABC, am I showing that AB is congruent to AC? Am I showing two sides congruent there? So that's the if part, right? The conclusion said that the side or the angles opposite should be congruent. Well, B is opposite AC and C is opposite AB, so these should be congruent. And that's what the conclusion of the theorem said. So we're going to prove that this is the case no matter what isosceles triangle we look at. This should always be true. Okay? So I'm going to write my given. Now I'm going to write AB is congruent to AC, and that's given. Draw out my picture. Now, do you guys remember a couple weeks ago, it was when we tried to prove the triangle angle sum theorem, said 180 degrees in a triangle. We had to add an auxiliary, I can't say that word, auxiliary line. I have trouble saying that word and rural. I said rural good.
Why do you-
I don't know.
No.
I know. Don't you have trouble, like rural, like who makes that word up? Like rural, like, yeah. That's I had troubles. I was in speech therapy when I was little. My R's and my L's got mixed up. Miss Baker, she fixed me. All right, so we had auxiliary. I can't say. We had this extra line, and we know it exists. Correct? We know that blue line exists. Okay, and I want to create it in a way that it. Would you guys agree that it is interacting in some fashion with this angle A up here? Okay, so I could draw it however I want. I could draw this ray here, or this segment. I can draw it like that, right? Or I could draw it like that. I can draw it over here like that. But would you agree that there is one in there, one segment or ray? Oh, I don't want to draw that. One segment or ray that does what to that angle A? Maddie? It bisects it, okay? So step 2 here, I'm going to state that we are going to construct just call this segment AM. Construct AM so that it bisects angle A. Okay? And it's basically saying that we know that line exists. Okay? We know every angle has a bisector, right? So we add in that angle that exists, or that segment that exists as a bisector, because there's no way of let me say, how can I word this? It's an absolute. It's an absolute truth. It has to exist. Okay. Okay. So if we do that, what does the word bisects in regards to an angle? What does that do for us up here? What does it do to those two angles? Makes those two angles congruent. So let's say that angle BAM is congruent to angle CAM. And that was because we introduced this word about bisect. We introduced an angle bisector. So those two angles are congruent because of the definition of an angle bisector.
To a parking lot
So we've got these two angles now congruent, right? Okay, now, remember when we drew this line right here, we didn't mention this, but when I drew that line, it took the original triangle and broke it up into two smaller ones, right?
Yeah.
What I'm trying to do here is try to initially show that these two smaller triangles are actually congruent to one another. So going off of our four congruency tools, whether they be theorems or postulates from the last couple days. Okay, now I've only got two of the three components that I need, but what would be a strategy here to show that these two triangles are congruent? Okay, so let's use side angle side. Why would you choose side angle side?
Because we know that AB and AC are congruent. So AC and then that angle that we found for the bisector and then the actual bisector.
Okay, so you're saying that the bisector AM is part of both triangles, right?
Yeah.
Okay, so AM is going to be congruent to itself, AM, through the reflexive property. And we see then that those two triangles, triangle BAM again, congruent to triangle CAM, are congruent, like you said, by side angle side. Is that something we can do? Now, what were the base angles? Of the original blue triangle, the base angles were angle B and C, right? Is B, does that correspond or match up to C in the names? So can I say in step 6 that angle B is congruent to angle C? By that phrase, CP, CTC, corresponding parts of congruent triangles are congruent. And now think about, we've matched up what we wanted to prove. That's the last line, so we're done. But think about what we started with. We started with an isosceles triangle. And now we concluded that the base angles are congruent. And that's going to be true now for every isosceles triangle that we come across. So maybe that's something, did you guys know that before you came to class? Did you know base angles were congruent in an isosceles triangle? You ever seen that before? Okay, some heads bobbing yes, some no. If you knew that, awesome. But you probably didn't know why, right? And that's really what I'm interested in us being able to decipher in a math class. You're going to come across all types of math as you move through the next couple of years, whether it's with me or another teacher, that you already know how to do, but you don't know why you know how to do it. You don't know what allows you to do those things. And when you have a class with me, that's what I'm interested in. Because if you can understand why and what governs those procedures, you're going to understand those procedures so much better. Okay? So what do you guys know about opposite sides of a parallelogram? They're equal. They're congruent. Okay? You know why?
Because there's people told
Two
us.
separate parallels.
So we're going to get there, but the why is something very similar to this. What we do is we take a parallelogram and we draw a diagonal in it. If you take a parallelogram and you draw a diagonal in it, so a diagonal is a line that connects two vertices that are non-consecutive. So two vertices that are not one after another, right? So if I have like segment or point A, B, C, I should probably write C down here. C and D. If I look at segment or point A, vertex A, B, angle B would be consecutive to it. It's right next to it, right? D would be consecutive. C is non-consecutive. So that would be a diagonal. Does that make sense? When I do that, what did I just create? Two triangles. What do you think that we're going to do when we want to show that the opposite sides of the parallelogram are congruent? What do you think we're going to first do with those two triangles?
Cut it in half. Like, make it two triangles.
Okay, we'll make it two triangles like that, but what am I going to say about triangle 1 and triangle 2? Or what do you think is going to be? We're going to be able to show that those two triangles are congruent. And because those two triangles are congruent, then CPCTC will allow me to say eventually that that segment and that segment are actually congruent. So opposite sides of a parallelogram congruent. And it'll allow me to do the same thing with the top and the bottom. But you know that the reason that is true, it's not that just somebody said that is a fact that we're always going to assure people of and make sure that happens when we draw parallelograms. It is a result of being able to take that figure and break it up into two triangles and learn that those two triangles are congruent and then byproducts of that congruency. Essentially everything that you guys probably know already about shapes, little features and characteristics that we haven't discussed. The reason you know them to be true is because that overall shape can be broken down into triangles. Okay, so everybody always asks, now, I thought this was geometry. All we do is talk about triangles. It's because if we learn a lot about triangles, they are the building blocks for learning stuff about other shapes. Okay. Some corollaries that we've kind of already talked about some of this stuff. An equilateral triangle is also equiangular. Equilateral is also equiangular. And the reason for that, think about this. If it's equilateral, you know it to be what? Also, what did we say at the beginning? I saw. So let's say I draw this shape here. Try to make it as equilateral as I can. So if it's equilateral, you know this to be true. That's the markings, right? Let's remind ourselves that it is equilateral, and we can do this a couple different ways. It's equilateral, but I'm going to take that marking out. What would be the angles that are opposite here of the two sides that I have marked? A and B, right? Those two have to be the same, correct? Those two have to be the same. Okay. Well, if I look at these two markings, because that one is equilateral, so that marking was there, right? Now which two angles would be the same? B and C. So now they should all have one mark in them, right? Does that make sense? Does that show you that they're all three the same? And if they're all three the same, 180 divided by 3 then is 60, correct? So equiangular triangles are equilateral and equilateral triangles are equiangular. And that stems from knowing that an equilateral triangle is at its foundation isosceles. And all that matches up. We can call this, now here's the issue with equilateral. Okay, those two angles A and B, those are the base angles if C is the vertex angle. Okay, but if A is the vertex angle, then does it make sense that these two over here, C and B, would be the base angles? Does that make sense? So with an equilateral triangle, a base angle can be identified as a vertex angle and vice versa. Okay. Usually when we do this with equilateral triangles, you're going to identify what you want your vertex angle to be. And then once you identify that, then it labels automatically your base angles. The bisector of the vertex angle, this one here is a huge tool for us for the rest of the year. It says the bisector of the vertex angle of an isosceles triangle is perpendicular to the base at its midpoint. Okay? And we'll come back and look at that red phrase here in a moment. But let's think about this. They're talking about this segment here, AM. We already know, we have already talked about these two triangles here being congruent, right? Okay? So those two triangles are congruent. Would you guys agree that based on the congruency, that this angle right there and that angle right there are congruent angles? They're corresponding angles, right? Based on those two angles being adjacent and forming that line right there, what do you know additionally about those two angles? Okay, so they form a linear pair, so they're supplementary. So then if they're the same and they're supplementary, you're telling me each one of them is 90 degrees, right? So if each one of them is 90 degrees, what does that tell you about AM? What does it tell you about AM, which would have been this angle bisector? In comparison to BC, it tells you it's perpendicular to BC, right? Okay, so going back to this phrase down here, it says the bisector of the vertex angle, that's that segment AM we're talking about, okay? And then it says is perpendicular to the base. Perpendicular to the base. But it's perpendicular to the base at the base's midpoint. Well, let's think about this. If we had triangle BAM was congruent to triangle CAM, is B to M first letter, last letter? Is C to M first letter, last letter? So we got BM congruent to CM. Is that okay with everybody? Well, if BM is that segment and CM is that segment, and we just showed them to be congruent, doesn't that by definition mean that M has to be in the middle of B and C? So M has to be a midpoint.
So could you also use side to
Yeah, so once you start filling this other stuff in, then you can justify, those are congruent, that would be congruent to itself, and now you can say these two triangles are also congruent by side, yes. But here's where this gets us to, okay? Is whenever you are looking at an isosceles triangle, whenever I look at an isosceles triangle, so let's say this is isosceles, okay? And you bisect this top angle, then when this bisector comes down here, it's going to find the midpoint of the base, so it's going to automatically do that, and it's going to be perpendicular to the base. Does that make sense? Okay, so that is one result of that corollary. Another one is if I start with my isosceles triangle, okay, and you have a segment like this, and they tell you it's perpendicular, then from that, you automatically know, well, if it's perpendicular there, then this had to be true. That has to be a midpoint. Does that make sense? And if those are true, then you have to know that this is also a bisector, okay? So when we have this thing here, we're on an isosceles triangle, we have really three conditions that are happening here. We have a midpoint on the base. We have perpendicular lines or right angles. And we also have an angle bisector at the top, at the vertex. If you have one of those things, any one of those, automatically the other two come into play and are true. So if I were to tell you this image right here, isosceles triangle, and I tell you that these two segments down here are congruent. So that would tell you that that's a midpoint, right? So that would tell you that this is true. So that automatically means that these other two are true as well. So that would be a right angle, and this set of angles up there would be congruent. Okay, is that okay with everybody? And that is what this phrase right here says: the bisector of the vertex angle is the perpendicular bisector of the base. Bisector of the vertex angle is the perpendicular bisector of the base. That's the best way of saying it. Perpendicular meaning right angle, right? And bisector meaning you have two congruent segments. Is that okay with everybody? We'll use that fact a lot as we move through the rest of the course. Converse of the isosceles triangle. See what the converse does? The converse says you take the if part and the then part and you flip-flop them. Okay? So we do have a theorem here that the converse is true for. So we could actually take the original isosceles triangle theorem and this theorem and write them as an if and only if statement. Okay, a biconditional. What this says, if you know two angles are congruent, in a triangle, so we're starting off with this information here, that angle B is congruent to angle C, then look opposite them. So opposite angle B would be segment AC, and opposite angle C would be AB. That is the conclusion. So if you know, right now, based on these two theorems, if you know you have an isosceles triangle theorem, if you know you have an isosceles triangle, the isosceles triangle theorem says that base angles are congruent. If you know you have base angles congruent, it tells you have an isosceles triangle. So it's a two-way street based on whether you got the segments congruent or you got the angles congruent. Does that kind of make sense? Okay. Some textbooks, I don't care, guys, whether you'll have to do it on some drop-down windows in Math Excel, but I don't care as we go through our discussions if you can remember which one's the converse and which one's the actual theorem. What I want you to understand is that if you have base angles congruent, then the sides opposite are congruent. Okay, if you have sides opposite congruent or sides congruent, then the angles opposite are congruent. Okay, you guys remember the other day when we started saying, like if I had a scalene triangle, you could start putting the segments in order or the angles in order. So let's say that I have a see if I don't know if I still have reset my computer today, so I don't know if I still have GeoGebra installed. Yep, just reset it. Reset my profile. I think it fixed it though. Okay, so I've got this triangle here. I know it's kind of hard to see at the moment. Remember being able to take those angles, their measurements, and then determine which segment was going to be biggest and which one was going to be smallest and all that kind of stuff? Okay. Let's do this. I'm going to put these distances in here. Get rid of this perimeter one. Okay, so I got those distances. And we said because this angle here was the smallest, then opposite it would be the smallest side. And we can confirm that, right? 7.63 is smaller than these other two, right? What if we were to take and rearrange things? So I've got now a triangle. It's starting to look a little bit more isosceles, right? Okay, let's do something like that. A little bit more isosceles looking, but we still have scalene. This is now the smallest angle, and that's the smallest side, so opposite. Let's do this. Okay, as I start moving this point C to the right, this angle should start to diminish, and so is this one, right? And let's actually put these all kind of at a grid here. Let's go move this one back in. There we go. What happened now? If those two angles just became the same, then the two sides just became the same, right? Okay, so there's a connection, and I know that was a 45, 45, 90 right triangle, but it doesn't have to be, it could both be 40.6 in this case, and we see that the sides are still congruent. Okay, so the idea is what we talked about the other day, about a week ago, being able to order the sides based off of the angles. Well, if the angles are the same, then the two sides have to be the same. And that's kind of a direct link to this idea with the isosceles triangle theorem. So something we can work with. What they ask you to eventually do is just like anything else when we've dealt with a congruency statement, where I talk about these, is that they'll do something like this. Okay, we've developed a theorem that establishes a congruency, which ultimately establishes an equality statement, and now they'll give something like this. They'll say, what's the value of x? Well, what do you know about the segment that is represented by 3x plus 6 compared to the segment represented by 7x minus 10? They're good. Because the angles are congruent, the sides opposite are congruent, so 7x minus 10 should equal 3x plus 6. Does that make sense? Okay. Now, what I would be cautious of, because I do this intentionally, and this is the reason I don't like Math Excel so much. I think Math Excel is a great program, but I also think that sometimes it lets people navigate through and be successful without really knowing what they're doing. Because if I come across this problem in Math Excel and I have absolutely no clue what I'm doing, could I maybe default back to say, well, I'll just take 7x minus 10 equals 3x plus 6? And, I've probably got a pretty good chance of getting this right, without understanding that concept. So what I do on tests and quizzes is I'll do something like that. Now you can't just grab any two of them and say any two of them equal, right? Now you got to know the isosceles triangle theorem, the converse, in order to establish which two expressions is said equal each other. Okay, so kind of be on the lookout for that kind of thing. They'll do it with angles as well. So this one here says measure of angle 2 equals x plus 138. So let's go through and find out everything we know about this set of triangles. Okay, first of all, if I look at this triangle here, okay, what kind of triangle is it? It's isosceles, right? Okay, so it's isosceles. So what's that tell you about this angle in comparison to that one? They're the same. So 34 removed from 180 is what, 146? What's half of 146? 73. So 73 and 73. What I want you guys to understand is that just because this has one mark in it, that has one mark in it, that does mean that these two angles opposite are 73, but it does not mean that every single angle opposite one mark is 73. So when I come over here, this is not 73. Does that make sense? Okay, because I'm into another triangle. And that should make sense because 34 and 73 don't add up to give me 90, right? But what does add up to give me 90? Say it again? 56. So that's 56. So what is this angle here? 56. What is this angle here? That was 112, right? It was 68. It's after 180. Okay. Can I find angle 2? How many different ways can I find angle 2? What does angle 2 have to be with that angle? They have to be supplementary, right? Okay, so it's got to be 124. Does that make sense? Okay, so measure of angle 2 is got to be 124. Could I have also said that angle 2 should be the sum of those two? You guys remember saying the exterior angle is equal to the sum of the two remote interior angles? So if, I don't know why I wrote a 5 there, it's 124. If it's 124 is one value for measure of angle 2, and you have this as an expression for that value, can I say x plus 138 is equal to 124? X then will be what, negative 14? Can I have x to be negative? Is that okay? X can be negative. Angle measurements cannot be, right? That's where we run into issues. So this is fine. That's the value for x in this situation. We feel comfortable with these two theorems? Okay, I want us to be able to use the theorems, but I want us to realize that they come from congruent triangles. Without the knowledge of congruent triangles, really all of Euclidean geometry from here on out does not exist or cannot exist. Okay, so that's